Discrete Fourier Transform Part 3. First is filtering using DFT, that is filtering using discrete Fourier transform. In practical applications, we often come across a linear filtering of long data sequence. DFT involves operation on block of the data. The block size of the data should minimize because digital processors have limited memory. So there are two methods of filtering: overlap save method and overlap add method. Now the first one is overlap save method. In signal processing, overlap save is traditional name for an efficient way to evaluate the discrete convolution between a very long signal x of n and finite impulse response filter h of n. In this method, the size of input data blocks is capital N, which is equal to L plus M minus 1, and the DFTs and the IDFTs are of length L. Each data block consists of last M minus 1 data points of the previous block followed by L new data points to form a data sequence of length L plus M minus 1. An n-point DFT is computed for each data block. The impulse response of the FIR filter is increased in length by appending L-1 zeros, and an n-point DFT of the sequence is computed once and stored. The multiplication of n-point DFTs for the mth block of the data is ym of k equal to hk into xm of k. Since the data record is the length of n, the first m-1 points are corrupted by aliasing and must be discarded. The last L points of ym of n are exactly the same as the result from linear convolution. To avoid the loss of data due to the aliasing, m-1 points of each data record are saved, and these points become the first m-1 data points of the subsequent record. To begin the processing, the first m-1 point of the first record is set to 0. The resulting data sequence from IDFT are given, where the first points are discarded due to aliasing and remaining L points constitute the desired result from linear convolution. This segmentation of the input data and the filtering of the output data blocks together form the output sequence. So the steps for overlap save method: step 1 is determine the length m, which is the length of impulse response data sequence, that is h of n, and determine m-1. So here the length of the input data block is capital N and it is equal to L plus M minus 1. So the n-point DFT is computed for each data block. Then the step 2 is the given input sequence, that is x of n, with size of DFT is n. Assume that n is equal to 5. So by appending L-1 zeros, the impulse response of FIR filter is increased in the length and n-point DFT is calculated and stored. Then step 3 is determine the length of new data L by using this equation, and the step 4 is pad L-1 zeros to h of n. So this is the input data sequence x of n, which is divided into number of L. Here x1 of n, x2 of n, x3 of n and x4 of n having m-1 data. Then the next is perform circular convolution of hn and block x of n. So y1 of n equal to x1 of n, circular convolution h of n. Similarly y2 of n equal to x2 of n into h of n, y3 of n is equal to x3 of n into h of n, and y4 of n equal to x4 of n and hn of n. Now values of these y1n, y2n, y3n and y4n can be given by like this, that is having first m minus 1 data, then y1 of n data, next is m minus 1 data, y2 of n data, next is m minus 1 data, y3 of n data, and next is m minus 1 data and value of y4 of n data. Then these y1 of n, y2n, y3n and y4n, these are the final output data sequence of y of n. So here the concept is to compute the short segments of y of n of an arbitrary length L and concatenate the segments together. Consider a segment that begins at n is equal to kl plus m for any integer k. The advantage is that the circular convolution can be computed more efficiently than the linear convolution according to circular convolution theorem. Now the overlap, discard are less commonly used labels for the same method described here. However, these labels are actually better to distinguish from overlap add because both methods save but only one discard. Overlap save algorithm can be extended to include other common operations of the system. Additional IFFT channels can be processed more cheaply than the first by reusing the forward FFT. Sampling rates can be changed by using different sized forward and inverse FFTs. Frequency translation can be accomplished by rearranging frequency bins. So here is the example for overlap save method. Now given that xn is equal to 3 minus 1 0 1 3 2 0 1 2 1 and h of n is equal to 1 1 1. So we will consider n is equal to 5. Then the length of hn is denoted by m and its length is 3. So m minus 1 is equal to 2. And we know that n is equal to L plus m minus 1. So by using this equation we can find the value of L. So here we get value of L is 3. Now pad L minus 1, that is 3 minus 1, that is 2 zeros with h of n. So the h of n will be 1 1 1 and 0 0. Now the sequence will be like this, that is above sequence is x of n, that is 3 minus 1 0 1 3 2 0 1 2 1. Now x1 of n is add, here we get the here we get the 2 zeros and we have to pad it. So 2 zeros, that is m minus 1, value of m minus 1 is 0 0 3 minus 1 0. x2 of n is minus 1 0, that is above values 1 3 2. x3 of n is 3 2 above values 0 1 2. This 0 1 2 is nothing but the number of new data, that is L is equal to 3, and this 3 2 is nothing but the number of previous data, that is m minus 1. Similarly x4 of n is equal to previous data 1 2 and new data 1 0 0. Next is performing yk of n equal to xk of n circular convolution h of n. Now what is the value of k? K is nothing but 1 2 3 4. Here we have to find the 4 values y1 of n, y2 of n, y3 of n and y4 of n. That is, we have to make the circular convolution of x1 of n with h of n. Now value of x1 of n is 0 0 3 minus 1 0 and value of h of n is 1 1 1 0. So output, that is value of y of n, will be minus 1 0 3 2 2. Value of these all values are performed by using circular convolution. Value of y2 of n is 41046. y3 of n is 67533. y4 of n is 13431. Now the next is we have to specify this value in this format. So n is minus 2, minus 1, 0, 1, 2, 3, 4, 6, 7, 8, 9, 10 and 11. Now we get the values of y1 of n as minus 1, 0, 3, 2, 2. So we write here y2 of y1 of n is 41046, y3 67533 and y4 of n is 13431. Now we discard the previous two values from y1, y2, y3 and y4. So we get the final output as y of n is, next three values are 3 2 2, next is 0 4 6, previous two values, that is 4 and 1, is discarded. Now the next is 5 3 is 3, that is 6 7 here discarded, and next is 4 3 1, and so here 1 and 3 is discarded. So the final output y of n is 3 2 2 0 4 6 5 3 3 4 3 1. Next is overlap add method. In signal processing, overlap add method is an efficient way to evaluate discrete convolution of a very long signal xn with finite impulse response FIR filter h of n. So y of n is equal to xn into h of n, that is circular convolution h of n. The concept is to divide the problem into multiple convolutions h of n with short segment of x of n. The linear convolution y k of n is 0 outside the region, and for any parameter having value n greater than equal to L plus m minus 1, it is equivalent to the n point circular convolution. The advantage is that circular convolution can be computed more efficiently than linear convolution according to circular convolution theorem. So in overlap add method, the input data block size will be L. So the size of DFT and IDFT having the same equation, that is n is equal to L plus m minus 1. So the first step is determine the length of n, which is the length of impulse response data sequence, that is h of n, and determine m minus 1. Second step is given input sequence x of n, that is size of the DFT, capital N. So here also we assume n is equal to 5. Now the next step is determine the length of L. The next step is pad m minus 1 zeros to x k of n and L minus 1 zeros to h of n. In the previous method we pad only L minus 1 zeros to the h of n. Here we have to pad both zeros, that is add both the zeros for both m minus 1 as well as L minus 1. So the input data sequence will be x of n. So x1 of n m minus 1 zeros, x2 of n m minus 1 zeros, x3 of n m minus 1 zeros, and x4 of n m minus 1. Next step is perform the circular convolution of h of n and block x of n. So y1 of n equal to x1 of n, circular convolution hn, y2 of n, y3 of n, and y4 of n. Find the values of all these. Then write the sequence in the in this form, that is y1 of n m minus 1 data, y2 of n m minus 1 data, value of y3 of n m minus 1 data, and y4 of n m minus 1. So here also we consider the previous example values, that is x of n is equal to x of n is equal to 3 minus 1 0 1 3 2 0 1 2 1, hn is 111. This method is similar, previous method starting method is similar. So n is equal to n minus, so consider n is equal to 5. Length of hn is nothing but the value of m, that is equal to 3. So m minus 1 is 2. We will find the value of l, that is 3, and here we pad the l minus 1, that is 2 zeros with hn. So hn will be 11100. Now here in overlap add method, the next step is different from the overlap save method. First, the input sequence, that is xn, can be written as it is, that is given sequence 3 minus 1 0 1 3 2 0 1 2 1. Now in overlap save method, we save the previous data before the x1 of n values. Now here we add the data, that is here we add the m minus 1 zeros after values of x1 of n. So first value of x1 of n is 3 minus 1 0, then add 2 zeros, m minus 1 zeros, that is 0 0. Similarly, value of x2 of n, add 2 zeros, that is 0 0. Now values of x1 n, x2 of n, x3 of n, this is nothing but the new data, and values of m minus 1 0 is nothing but the number of zeros we add. Now the next is performing the circular convolution. So we use the circular convolution. y1 of n is equal to x1 of n into hn, y2 n equal to x2 of n hn, y3 n equal to x3 of n hn, and y4 n is equal to x4 of n h of n. So we find the values of all these by using the circular convolution. The next is put these values of y1n, y2n, y3n, and y4n in this format. So we put here these values and add m minus 1 data here. Now so here we write y1, y2, y3 and y4 of n values here, and we will find the final output sequence y of n. So the final output sequence y of n will be values of y1 of n with 3 bits as it is, then add values of y2n with m minus 1 data, and this addition will be like this. Next is add y3 of n data with above m minus 1 data, the output can be written in y of n. Next is y4 of n will be added with m minus 1 of the previous data, output will be written as it is, and the next is m minus 1 data as it is. So this will be the final output sequence. Now amplitude spectrum and power spectrum. The FFTs and the power spectrum are useful for measuring the frequency content of the stationary or transient signal. The next is introduction to discrete cosine transform. A discrete cosine transform expresses a finite sequence of the data point in the terms of sum of cosine function oscillating at different frequencies. The discrete cosine transform, that is DCT, helps separate the image into parts or spectral subbands of differing importance. The DCT is similar to the discrete Fourier transform, but it transforms a signal or image from a spatial domain to the frequency domain. Thank you.